non si focalizza un attimo. Sì, no? Che si vede. Okay, so last time we were starting to see the properties of a Fermi gas at zero temperature, and you know what I'm talking about, so I will not go too much into the details. Basically, the starting point is to observe that the Fermi distribution becomes a step function, a Heaviside function, in which all the levels of the continuum are occupied until a certain value, which is the Fermi energy, which is equal at t equals 0 to the chemical potential, and that's it basically. So the integrals are very easy in this case because one can just use the fact that the distribution becomes a constant apart from 0 to the energy, the Fermi energy, and that's it. Okay. So we saw last time already the some of the relations that characterizes a Fermi gas at zero temperature. One of them is the relation between the density and Kf, which is the Fermi momentum. I think here there is a 6. And G is a degeneracy factor, 2 for the case of spin 1/2 particles, for instance, for electrons. The Fermi energy is equal to mu at t equals 0, and Kf and the Fermi energy are related by the relation that Kf squared, h squared divided by 2m is equal to the Fermi energy. This is the density. That's it. Notice that mu is larger than 0. Because mu is the Fermi energy, and the Fermi energy is basically this quantity, which is a kinetic energy. So mu is larger than 0, which is very different with respect to the case of bosons and the case of classical particles, for which the chemical potential was negative in the case of classical particles. For bosons, is strictly less than 0 and is equal to 0 in the Bose-Einstein condensate. Whereas here it is larger than 0. Okay, that's opposite with respect to classical and Bose and bosons. We will plot the behavior of the chemical potential later, and we will compare all of them. Okay, so the interpretation is that, as I said before, all the levels of the continuum are occupied. This is Kx, Ky, and Kz, and this is the Fermi sphere, which is all occupied by particles, and then all the other particles, all the other levels are unoccupied. Okay, so that's it basically. Now, this is the relation between, if you want, density and chemical potential, because the chemical potential is in here, basically Kf. Now, what we need to do is to compute the equation of state, and to compute the equation of state, we need to compute the logarithm of the grand canonical partition function, and then, for instance, if we want to compute the internal energy, we have to do the minus derivative with respect to beta of the log of the grand canonical partition function, which in this case is the following. Let me write here the log of the grand canonical partition function. This is g b 2 pi squared, an integral from 0 to plus infinity dq squared log of 1 plus z. Then I have E minus beta epsilon q. Okay, so this is the log of the grand canonical partition function. So now I have to compute the derivative with respect to beta of this quantity, basically. Okay, so here I have gv 2 pi squared that I can put outside, gv divided by 2 pi squared. Then I have to do the derivative of this quantity, which with respect to beta. So let me see, I have an integral 0 to plus infinity dq q squared. Here I have 1 plus z e minus beta epsilon q. I'm deriving with respect to beta. So then I should have here z exponential of minus b epsilon q, and then minus epsilon q, which becomes plus epsilon q, considering the fact that I have a mixed variable. Okay, and basically that's it. Now I need to multiply by z to the minus 1 and e to the beta epsilon q. And in this case, I have the standard result, no? So gb 2 pi squared, blah, blah, blah. Okay. Let me see if I have all the factors. Yes. So, now, from this, I can multiply by z minus 1 and e plus beta epsilon q. Therefore, this becomes 1, this becomes 1, and this becomes the usual factor, which is the following: gb 2 pi squared integral from 0 plus infinity of q squared epsilon q, and here I have the derivative, which is beta epsilon q minus b plus 1. Okay, which has the simple interpretation that here I have the energy, and here I'm integrating this energy times the distribution. Okay, so it's the standard interpretation. And this is the probability of having a certain energy, and then I integrate the energy times the probability to get the total internal energy. Okay. Now this function here, as we said previously, e to beta epsilon q minus mu plus 1, 1 over, becomes a theta function for t going to 0 becomes a theta function. And this theta is the following: mu minus epsilon q. Okay, in the limit in which this is equal to 0. Therefore, at t equals 0, u becomes g v 2 pi squared. Then I have the dq q squared h squared q squared divided by 2m, and then I have a theta function of mu minus epsilon q. Okay. Well, that's it. Now one has to do the integral. So this is g v divided by 2 pi squared, dv divided by 2 pi squared. Then I have h squared divided by 2m, h squared divided by 2m, and then I have q to the power of 4, which means q to the power of 5 divided by 5, which is this value of q is the Fermi momentum. Okay, so then it becomes kf to the power of 5 divided by 5, and then I think I have everything. Bg 2 pi squared h squared kf. Yeah, this is internal energy as a function of the Fermi momentum. And let me compute U divided by N, where N is the number of particles, so the energy per particles, if you want. And I have the same expression as before, so G V 2 pi squared H squared divided by 2M AF to the power of 5 divided by 5. And here instead N is G V 2 pi squared. And here I have a Fermi momentum cubed divided by 3. Okay. So now I have the usual 3 divided by 5. So this is 3 divided by 5, because this drops. I have a Fermi momentum to the power of 2, which becomes a Fermi energy. And so I have times 1 over 2m, and this becomes 3 divided by 5, the Fermi energy. Okay. This is the energy per particle. This relation, you might remember this, right? Maybe from previous lectures. Okay. This is the energy per particle. Okay, one can go on and compute all the other quantities. In particular, one can compute the pressure. We have the internal energy, we can compute the pressure. How does the pressure relates with the grand canonical partition function? Well, the pressure is basically the following, can be obtained by the following equation. Z of G is e to the minus omega beta, where omega is the ground potential. Therefore, the log of Zg is the minus omega beta. And what is omega? Omega is minus dV. Okay. So therefore, here I have P V beta, which is equal to the log of Z of G, from which the pressure P is equal to kBT divided by volume, and then I have the log of Zg. Let me check if this is correct. kBT, yeah. One can again compute this quantity, starting from the log of Zg that we derived before, or one can do it more quickly in the following way. And basically, one can use this relation. Maybe it's the easiest way to do it. Otherwise, it's a little bit boring. Vediamo se c'era un modo di farlo così, sì. I can use this relation as in the case of bosons, for which we have derived the result. Here we find again that the relation between pressure, volume, and internal energy is the classical one, corresponds to the classical one. Namely, PV is equal to 2/3 U. Okay. How does it come from? Basically, I take this expression, I make an integration by parts, and then I get this factor 2/3 in internal energy. As in the case of bosons, nothing changes, but for the fact that I have a +1 in the denominator, whereas in the case of bosons, I had a -1. And for the rest, it's the same. Okay. So then I can use this relation and make the following trick. So here divide by the volume. So this is 2/3, and let me multiply by n, numerator and denominator. So you have n divided by the volume and u divided by n. And let me see So here I have 2/3. U divided by n is the relation that we derived before, which is 3 divided by 5 the Fermi energy. Whereas, yes, then I have a density, right? Then I have just a density. This is the density, n divided by the volume, okay? So you have 2 divided by 5 Fermi energy times n, and this is the pressure. Okay? So P is equal to 2 divided by 5 Fermi energy times the density. And as you see, here I have as opposite to the case of, well, for a classical particle, suppose that I can extrapolate the equation of state of the ideal gas to T equals 0. I have PB is equal to KB and T, and therefore at T equals 0, the pressure will be equal to 0. In the case of bosons, we know that at T equals 0, all the particles are in the ground state, and we know that in the ground state, there is no for the ground state, there is no contribution to the pressure. So the pressure will be equal to 0, also in the case of bosons. Whereas here, we are at T equals 0, and we find that the pressure is strictly positive. And what is this pressure is the Fermi pressure. Or is the also the degeneracy pressure, which is present even at T equals 0. Okay, this basically due to the Pauli exclusion principle, and this is of course a very remarkable fact. You know some examples in which the Fermi pressure is important in real systems. Are you aware of any system that is in astrophysics is full of objects in which the Fermi pressure is could be the dominant contribution? For instance, for white dwarfs. White dwarfs are basically stable because of a balance between gravity and the Fermi pressure due to the electrons. Okay, so because they are T equals 0, which means not exactly that the temperature is small, but the temperature is small with respect to the chemical potential. It's a degenerate gas. Okay, so we have this situation, so with the high degeneracy, when the T is much smaller than the chemical potential. So now here we are at T equals 0. Then we will see the first order corrections later. But basically, the important point is that at small temperature of T equals 0, in any case, I will have a pressure. Okay, and this is the case for many astrophysical objects, so like white dwarfs or even neutron stars have an important contribution to the total pressure given by the degeneracy pressure of neutrons in that case. Okay, which is not enough to keep the star stable, but it's an important contribution in any case. Okay? So this is a very important concept, the Fermi pressure, because it's a quantum effect, because here it's quantum mechanics, we have T equals 0, that shows some effects on macroscopic scales as stars, okay, so as compact stars in particular. Okay, so I think that for this is enough. For T equals 0, now I think it's enough. And then we move on and we try to see what happens when we increase the temperature. So as in the case of bosons, we have done the classical limit, which is the one for which Z, the fugacity, approaches 0. That is the classical limit. Then we move on the other side and we see what happens in the quantum regime. And as in the case of bosons, the first thing one can do is to find out what happens at T equals 0 and then at T larger than 0 but small in any case. Okay. So now we will see one thing which is a little bit technical, but it's important because it allows us to find the behavior of the entropy and the heat capacity at small temperatures. And that, of course, is a quantum correction with respect to the classical result, which is called Sommerfeld expansion. Actually, from this expansion, we just keep the first two terms. Okay. So now let's work in the regime in which t is larger than 0 but small. What does it mean, small? Well, t much smaller than the chemical potential. The chemical potential is a positive number, as we said before, at t equals 0, at least at t equals 0, t small t. And therefore, if I take the fugacity z, which is equal to e to beta mu, since mu is a positive number and beta is 1 over kBt and t is small, that means that this function goes to plus infinity in this regime. Okay? As opposite to the case of bosons, for bosons, z was instead within this range, was varying within this range, which was 0 to 1, and 1 was the quantum limit in which I have a Bose-Einstein condensate. Whereas in this case, for t small, basically z goes to infinity. Okay, because now mu is a positive number, and if t is small, then this goes to plus infinity. Okay. This is an important fact because the limit in which we are working now is not the limit in which z is small, which is the classical limit, but for fermions is the limit in which z is approaching infinity. So we are going to make an expansion around infinity, if you want. Okay. Okay, good. So first of all, let me introduce a relation that we derived for bosons, and that is the same for fermions, but for the fact that we have a plus, and here we have a different function, which is the Fermi function instead of the Bose function. Okay, this is the integral from 0 to plus infinity of x squared e to x squared plus 1. See. Let me just find one thing. This is n lambda squared, no? Yeah. And lambda cubed. And lambda cube is f3 half of z, and this function here is the following integral representation. Okay. Now, as I said before, what we are going to do is to expand around infinity by considering the fact that the small temperature z is approaching infinity. Let me introduce a quantity which is called mu, which is the logarithm of z, which of course is also quantity for t equals 0, for t approaching 0. And now it's a matter of making some little bit technical calculation to see what happens. Okay, so let me start from this integral, and let me introduce a new variable. Well, first of all, f3 half of z is equal to 4 square root of pi integral 0 to plus infinity dx x squared, and here I have e to the x squared. Z minus 1 is exponential of minus mu, because e to nu is equal to z, and therefore z minus 1 is e to the minus nu. So therefore here I have a minus nu plus 1. Okay. And here I can make a similar argument. I can use a similar argument to the one I used before for the Fermi function. The Fermi function becomes a step function indeed when t is small, and here instead I can work with nu. When nu is large, this will become a Heaviside or a step function. Okay. Now we see how to treat it. First of all, let me introduce a quantity which is y, which is equal to x squared, and for 2y dy, so it's 2x dx, and for square root of y is equal to x, and this integral now becomes simply right upstairs. So here I have f3 alpha of nu, because nu and z are basically one the log of the other one. And here I have a 4 square root of pi integral from 0 to plus infinity. Instead of dx, now I have substitute dy divided by 2x, which is the square root of y. Then I have an x squared, which is y. And here I have exponential of y minus nu plus 1. Okay, so this is equal to 2 and 4. I have a 2 square root of pi integral from 0 to plus infinity in dy of square root of this quantity here divided by e to y minus nu plus 1. Let me make an integration by parts of this quantity and get the following results. 2 square root of pi. Then I integrate for this term. This is this y to the 1/2, which becomes y to the power of 3/2. Then I have a 2/3, 1 y minus nu plus 1. This must be computed from 0 to plus infinity. And at y equals to 0, this is 0, whereas at plus infinity is 0 again because of this exponential suppression. So this actually is equal to 0. And then I have a minus integral from 0 to plus infinity of y to the power of 3/2. Then I have a 2/3 here. Then I have to derive this quantity, which is squared. I get a plus here. And exponential of y minus nu dy. And I think I have all the quantity correct. Okay. Now this is equal to 0, so that is close this bracket. So this is equal to 0. I have a 4 divided by 3 and square root of pi. And then I have this integral, which is 0 to plus infinity of y to third, y 3/2, sorry, y 3/2, y 3/2, e to y minus nu, and e to y minus nu plus 1 squared in the y. Now let's introduce another quantity. It's a little bit technical, this calculation, but once in a life means in life one has to do it because it provides the first correction at t equals 0 for t small. So let's introduce the quantity t, which is equal to y minus mu, dt is equal to dy. Therefore, the integral becomes 4 divided by 3 square root of pi, integral from 0 to plus infinity. Y, what is y is t plus mu to the power of 3r. And here I have e to the power of t. And here the denominator e to the t plus 1 squared in the t. Okay. Now, since mu is large, let me collect mu in such a way that I can do a Taylor expansion. So this can be written as 4 divided by 3 square root of pi, mu to the power of 3/2. Then I have the integral from 0 to plus infinity of et plus 1 squared. And here I have 1 plus t divided by mu to the power of 3/2 in dt. Okay. Let me check if this is correct. T più 1, 1 più t, blah, blah, blah. Good. Now, since mu is going to plus infinity, because we are expanding around infinity, I can expand this function here, which is 1 plus d divided by mu to the power of 3/2, which is equal, in the limit in which mu is large, to 1. I do a Taylor expansion. Then I have 3/2 t divided by mu. And the second term, that I'm not going to compute, but I'll tell you the result, which is 3 divided by 8 t squared divided by mu squared. Okay, last. I Taylor expand because mu is equal to, well, mu is going to infinity. Okay, so then in this expression, I can use now this expansion. Okay, so at leading order, which is 1, so if I stop at the first order, so first order, this function is just 1, and then I have 4 divided by 3 square root of pi, mu to the power of 3/2, and then I have the integral, which is the following, 0 to plus infinity, et dt, et plus 1 squared to first order. And this integral is actually equal to 1. Is equal to 1 because this guy here should be 1 divided to et plus 1 minus computed. Here I think I've done a mistake before. Sorry, because I have introduced that t was the y minus u. So I need to correct this. Then if y goes to infinity, and so this is plus infinity, but here, and this is an important trick, y is equal to 0, and t is going like minus nu, but nu is infinity, and so therefore minus infinity. It's important. T goes to plus infinity and goes to minus. Sorry, I forgot to tell this. And so that also this guy here is minus. So this is minus 1 divided exponential of t plus 1, and this must be computed from plus infinity to minus infinity, minus infinity plus infinity. Okay, so this is the primitive of this. Okay. So at plus infinity, I get 0, and at minus infinity, this is 0, then I have minus 1 with an additional minus, so becomes a 1. Okay, so actually it's equal. The leading order, I get 4 divided by 3 square root of pi due to the power of 3r. And this guy is actually my f 3r of z, or if you want. Okay. Cancello questo. I will use again the expansion later. Now, what is new? New is the log of z. So then I get this. If I want to write this in terms of z, f3 alpha of z is 4 divided by 3 square root of pi log of z to the power of 3 alpha. So, as in the case of the classical limit, in that case z was equal to 0, I was making an expansion of this function around z equals 0. Here I am expanding around z infinity. Okay, and the first term is a log term, log to the power of 3 alpha. Okay, now I can verify that what I have here is actually the same expression that I had before. Let me sketch the calculation. So basically, I have to use the fact that n lambda cube is equal to f3 of z. And now in this case, f3 alpha of z is this function that I just found. So it's 4 divided by 3 square root of pi log of z to the power of 3 alpha. From which I get that the log of z is 3 square root of pi divided by 4 and lambda cubed to the power of 2/3 log of z è questo affare qua. 3 square root of pi. Okay, great. Okay. Now this is equal. I can make a what I'm doing is to verify that well, at t equals 0, I get the standard formula. At t equals 0, I know that mu is equal to the Fermi energy, basically. Mu is equal to the Fermi energy. Okay. Well, to do it, let me introduce there some was 3 pi divided by 4. What is n? Okay, facciamolo così, 6 pi squared divided by 6 pi squared. Here you have a n, and then lambda cubed to the power of 2/3, which means lambda to the power of 2, and lambda to the power of 2 is a h squared. Questo lo faccio ancora dentro. is h cubed divided by 2 pi m kBt to the power of 3 half, and everything is to the power of 2/3. Vediamo se c'ho tutto, scusate. Now remember that n is equal to kf squared, sorry, kf cubed divided by 6 pi squared. Therefore, this quantity here is just kf cubed. Okay, so this is equal to 3 square root of pi divided by 4, and I have a kf cubed divided by 6 pi squared. Then I have a h bar cubed times 2 pi cubed. Poi che c'ho altro? C'ho tutto questo oggetto. Just a moment that I check all the coefficients. Yeah, is to the power of 2/3. And then I have outside, I have 1 divided by 2 pi and kBt. Ok, va bene. Vabbè. Now it's a matter of doing the calculation, but as you see here, I get a kf to the power of 2/3, which is a kf squared. Then I get here a 2m, and then I get another h bar squared, which is just the Fermi energy. Therefore, this quantity here, if I work out also the pi, how many pi I have here? I have a pi from here, pi to the power of 3 half, then to the power of 2/3 becomes a pi that cancels with this pi. And then let me check also how many 2 I have. So here I should have, here I have 24, and here I have 24, no? Because it's 8 times 3, and so this cancel. Okay, so all of this expression actually becomes equal, if you do the calculation, it's equal to the Fermi energy divided by kBt. This is the logarithm of z. You can also write this quantity as follows by introducing a new temperature scale, which is the Fermi temperature. That I name Tf equal by definition to Fermi energy divided by Kb, and therefore the log of Z is equal to the ratio between the Fermi temperature and T. And of course, this quantity goes to infinity as T is going to 0, no? Because Tf is a positive quantity, T is approaching 0, and therefore the log of Z is going to infinity. Okay? This can be derived also by considering the fact that the log of Z is the log of the exponential of beta mu, and therefore this is just beta mu, and this mu divided by kBt, and at t equals 0, mu is equal to the Fermi energy, just at t equals 0, then we see there will be a correction, and therefore I get that here I have Fermi energy again divided by kBt. is equal to TF divided by T. Okay? So this is another way to do it, which is much simpler, but I prefer to do both of them. Okay, so now we have to move on and see which are the contribution of the other terms of the expansion in log of mu. This was just the first one, and I get the result that I was expecting, that the relation between, well, basically this quantity here, EF divided by KB is the log of Z, which is the relation between mu and Fermi energy, which are the same at equal to 0. Now we need to move on. Let me write again the expression that I had before. So what I was trying to do is to see what happens to this function of mu when mu is large, minus infinity plus infinity dt, 1 plus t divided by mu, to the power of 3 half et plus 1 squared dt. And we said that 1 plus t divided by mu to the power of 3 half is equal to 1 plus 3 half t divided by mu plus 3 divided by 8 t squared divided by mu squared. Okay, so now the first order we have seen what happens. Now we go to the second order. At the second order, this function here will be, it's not the second order, it's the second term, okay, which is linear in here, okay, second term, the function. I would get an integral which is dt from minus infinity to plus infinity of et plus 1 squared. And then I have here a function which is t divided by mu. Okay. Now this integral is actually equal to 0 because this even function, which is this one, times a odd function, so therefore this is equal to 0. Fatemi provare a fare una cosa, e to the minus t and e to the minus t plus 1 squared. If I multiply by e to t, I have et, and here I have e to t, which is e to t plus 1. And you can verify that this is an odd even function of t, whereas this is an odd function of t before this is position. Okay. And indeed, actually, this function here looks like a sort of it's not a Gaussian, but it's like a bell. Okay. Okay. So this term does not contribute. Therefore, we have to go to the second order now in t squared. Okay. So we go to the second order in t squared, which is the third term in the expansion, and we will stop there. So let's go to the third term of the expansion, which is this one, third term. So I have a 3/8 divided by mu squared. And then I have the integral from minus infinity to plus infinity of dt of t squared exponential of t and et plus 1 squared. Ok? Diviso 8, no squared. Ok. Let me multiply the guy by e to the minus t. There is a trick to do it. Let me see what was the trick. Yeah. So if I do this, e to the minus t and e to the minus t half squared, then I can write this as a 3/8 mu squared integral from minus infinity to plus infinity t. Here I have a t squared here, whereas here I have, I can put this inside, and then I have e to the t half plus e to the minus t half, which becomes a hyperbolic cosine times 2 of t half to the power of 2, which becomes 4 cosine of t half squared. Vediamo se c'è tutto. Sì, c'è il 4 coseno, va bene. Okay, so now some other doing the integral, and I'm not going to compute this. dt is equal to y. Just tell you the result. Okay, so this is 3/8 mu squared. Then I have 3 powers of t. Therefore, I have 8. I should have 8 here. Integral of dy from minus infinity to plus infinity of y squared divided by cos squared of y. And I have an additional factor of 4. 8 quarti per quella fare là. Okay. Now this integral, I'm not going to do it. Actually, it's I think I've done it the second here. Well, actually, this was an exercise for the course on mathematical physics. One can do it with the residual theorem. I'm not going to do it. And this is equal to pi squared divided by 6. Okay, so then I have to collect all the results. I have 8 and 8 cancels. Then I have 3, and then I have a 6 there. So I have a factor of 8. It's a pi squared. So this is equal at the end is equal to pi squared divided by 8 mu squared. Okay. Pi squared divided by 8 mu squared. Okay. Now let me come back to the previous expression, and I'm almost done, I promise. Before we wrote that 4 divided by 3 square root of pi nu to the power of 3 half. Then there was this integral minus infinity to plus infinity of nu 1 plus t divided by nu to the power of 3 half. And et plus 1 squared. And this function here was the f3 half of mu. And we were expanding in nu in the ratio t divided by nu. The first order we had done, the second is the first term is done, the second is vanishing, it's vanishing. And the third one is the one that we have computed. I got that the integral is equal to pi squared divided by 8 mu squared. and then I have to multiply by this function, by this term here. Okay. So then I get the following expansion for the F3 alpha of nu. L'ho fatto. So the F3 alpha of nu or of z, if you want, the same, is equal to 4 divided by 3 square root of pi. Then I had here the first term was the term in nu, because the integral was equal to 1, and also the first term is the log of z to the power of 3 alpha. Okay. Plus pi squared divided by 8. Here I have 1 divided by nu squared, and here I have nu to the power of 3 alpha. 2 minus 3 alpha is 1 alpha, and therefore I have a log, a square root of log at the denominator. Square root of log. And this function, of course, is equal to n lambda cubed. Okay. So the expansion that I'm doing is similar to the classical one, but here log of z is large. Okay. Okay, so the leading term is this one, then I have this some leading term. Okay, now from this I can find the first correction to the relation between chemical potential and Fermi energy when I have a finite temperature, finite but small temperature. So it's a matter of doing the calculation. Today is like that, unfortunately. And so it's again the log of z to the power of 3 alpha is equal to 3 square root of pi divided by 4 times n lambda cubed. Then I have a minus pi squared divided by 8. Here I have 1 over the square root of log of z. This is the relation that I can find from here when inverting in order to find log of z. Okay. Okay. Now, from the previous equation, that was the following, we saw that previously, we saw that the log of z was equal to Tf divided by T. And also, we saw previously that the log of z, the first iteration, is equal to 3 square root of pi divided by 4 and lambda cubed to the power of 2 thirds from the first term. Okay. So actually this quantity here is just Tf divided by T to the power of 3 alpha. Okay? Because this quantity is log of z to the power of 3 alpha, but the log of z is Tf divided by T. So it's Tf divided by T to the power of 3 alpha. The first term. Minus pi squared divided by 8. And here I have the log of z is Tf divided by T from the first iteration, if you want, to minus 1/2. Okay. Okay, so now I can collect the first term. So this is equal to Tf divided by T, 3/2. And here I have a 1 minus 5 squared divided by 8. And here I have T divided by Tf to the power of 2. T divided by Tf. Let me check. Sorry, let me check if this is correct. If I get the right result. So this 3/2 minus 2, which is minus 1/2. Yeah, it should be correct. Okay. And this is the log 3/2 of z. Now from this I can get the log of z. Log of z is equal to Tf divided by T power 1, because I'm making the 2/3 roots. And here I have 1 minus 5 squared divided by 8, T divided by Tf squared, and then this to the power of 2/3. Okay. Okay, now T small with respect to Tf, which is a finite quantity. As T is small, I can use the expansion. So since T divided by Tf is very small, in the limit in which we are working, log of z is equal to Tf divided by T, and here I have 1 minus pi squared divided by 8. And then the 2/3 goes here, basically. No, I'm using this. Okay, so I get Tf1 pi squared divided by 8, and then I have a 2/3 here. To the power of 2. Which is finally here divided by T is 1 minus pi squared. Here I have 12, and the T here, that's it. Okay, almost done. From here, z was the exponential of beta mu. So therefore, the log of z is mu is beta mu, which is mu divided by kbt, and therefore mu divided by kbt mu divided by kbt is equal to Tf divided by T. And then I have 1 minus plus pi squared divided by 12. Okay. T and T drops. So mu is equal to kBTF. kBTF is just the Fermi energy by definition of Tf. And here I have a 1 minus pi squared divided by 12, T divided by Tf squared. Okay. Now, this is the relation between mu and Fermi energy, the first correction when we increase the temperature. So at T equals 0, mu is equal to EF, whereas at T finite but small, This is the first correction. Okay. First correction. The relation between and it is a quadratic correction in temperature. That's very important because this quadratic correction will be found also, for instance, in the other thermodynamical quantities, and therefore we can infer, for instance, which is the behavior, for instance, of the entropy at small temperature and the behavior of the heat capacity at small temperature when we have to do with fermions. Now let me sketch a plot of the chemical potentials, and then we stop for a break. Because it's 12:15. Sorry, today it's a little bit it's there are a lot of calculations to do it, but I know it's not a big story. Okay, so let me make a plot of mu as a function of the temperature. For the classical case, we have that m, so mu is equal to kBT log of n lambda cubed. So this is the classical one. Okay, the classical relation. And if you make a plot of mu versus t at fixed mu versus t at fixed n, which means fixed volume, fixed number of particles, then for the classical you get something like this, where the zero is found when n lambda cubed is equal to 1. Okay. So here n lambda cubed equal to 1, which is exactly the point at which, below which, we expect classical physics to break down. No? So this is the behavior of the chemical potential if one makes a plot as a function of the temperature. Now, what happens with the boson gas? With the boson gas, of course, at large temperature and fixed density, we need to recover the classical limit. So we will have a behavior like this. But then at some point we have deviation until a point here in which I touch the critical temperature for the Bose-Einstein condensation, which of course has a finite value of the temperature. So if I fix the density, I have a certain value of the temperature for which, below which we have the Bose-Einstein condensate, and then in that case mu is equal to -1. Okay, so here mu approaching 1 from the left, sorry, mu is approaching 0 from the left, which is the corresponds to the BC. Okay, so it touches this axis and then it stays constant to 0 chemical potential. What happens with, so this is for bosons, so this is for classical particles, classical. And what happens with fermions? So with fermions, we see that at t equals 0, we have that mu is equal to EF. So actually, it goes to a constant here, which will be EF. And then we have this quadratic correction. Of course, we will have other correction. We are not computing, but qualitatively, the behavior will be something like this. Which, of course, then I have to recover the classical limit. This is for fermions. And the point at which the Fermi result touches the axis is basically close to TF. So I need to put this equal to 0, no? And these are basically T almost equal to TF. So well, I need to compute this T, so this is 12 divided by pi squared and square root of, right? It would be the point at which the chemical potential is equal to 0. Well, actually, this by considering the first order correction, okay? Actually, when keeping all the other correction, the scale in any case is provided by TF, then some numerical factor, okay? Okay, so this is the plot of the chemical potential of the three cases, so classical, bosons, and fermions. Now we will see, but we stopped for a while, which is the correction that we have on the pressure and on the internal energy as due to the well, to this correction in T where that we have found in the chemical potential. Okay, so let's stop 5 minutes and then we continue. No, no, it's fine. Okay, so let's start again. So now what we want to do is to use the result for the chemical potential and so the estimate that we have done at first order, so the first correction to the t equals 0 case, and we see how this effect propagates into the equation of state. See what happens. So log of z was found before. It is equal to tf divided by t. And here you have 1 minus pi squared divided by 12. And here you have t squared. Okay, so I need to keep this relation because it will be useful in a moment. Then, now we ask ourselves, what is the correction to the equation state? Okay. And to do that, we need to consider the relation of the equation of state, which is the p lambda cubed divided by k dt is the f of phi 1 of z, which in turn is equal to 8 divided by 3 square root of pi integral from 0 to plus infinity dx. Then I have x to the power of 4 z minus 1 e to x squared, which is the Fermi function for phi alpha. Ok, blah blah blah, questo è 8 terzi pi greco. Okay, now the procedure is the same as before, so I'm not going to repeat it. So I introduce first mu is equal to the log of z, which is a large number. Then I need to introduce, so then in this way, this becomes s squared minus mu plus 1. So the first thing to do is this. Second thing is to introduce a quantity which is y equal to x squared. And well, by doing this, basically the same calculation we have done before, we obtain the following expression that I'm going to write. So the third point was to introduce a quantity which is t, which is equal to y minus mu. And t is going to infinity, from ranges from minus infinity to plus infinity. Because mu is large. And we see that this function here is equal to the following. So the f phi alpha of mu, by really repeating the calculations that we have done before, just that the prefactor are different, we get 8, 15 square root of pi, mu to the power of 5 alpha. And here we have the integral from minus infinity to plus infinity dt of 1 plus t divided by mu to the power of 5 alpha, and et plus 1 squared. Okay. Now, as before, one expands this function here. And so 1 plus t divided by mu to the power of 5 alpha is equal to 1 plus t divided by mu 5 alpha. plus there is the quadratic term, which in this case is provided by 15 divided by 8, that one can compute, of course, u squared plus other terms. So as before, 1, which corresponds to the t equals 0 case, the first correction does not contribute because this is linear in t, and we have to go to the second order in t in order to have the correction. Then if you do that, you see that the result will be 8 divided by 15 to the top pi, mu to the power of 5 half, then I have 1 plus 0, which was the linear term in t, plus the other correction is another integral, which is equal to 15 divided by 8, which is this guy here. And then we have again the same integral as before, which was the integral of y squared divided by hyperbolic cosine squared, which is the same integral as before. And here I have a mu squared and 5 to the power 3, exactly as before. Just as pre-factor now is different, and also this factor is different. Okay. So now the f5 half of z is equal to, okay, this guy here, which is 8 divided by 15 square root of pi log of z to the power of 5 half. Then I have inside 1 plus, qui mi viene un 5 ottavi, 5 divided by 8 y squared, and here I should have a log of z to the power of 2, minus 2, sorry. Quindi 5 ottavi log of z to the minus 2. Okay. So let me see if this is correct. Questo qui 5 mezzi, 1 è la correzione, 5 ottavi per squared. Good. So now the thing is that we need to substitute, instead of log of z, we have to take the expression that we had before. So the log of z is equal, as I wrote before, to pf divided by t, 1 minus y squared divided by 12. Yeah, that's correct. So I have to take this guy here and substitute here. So let me try to simplify as much as possible, because otherwise we do not finish neither today. Okay. So remember that the lambda cubed p divided by kbt is equal to f5 half of z, and the f5 half of z is equal to all this quantity here, okay? Which is 8, 15 square root of pi log of z to the power of 5 half is this quantity here. So it's tf divided by t, 5 half, and 1 minus pi squared divided by 12, t divided by tf squared to the power of 5 half. Okay, then I have 1 plus 5 divided by 8 pi squared. Then I have this quantity here to the minus 2, which is the tf divided by t to the minus 2, and then 1 minus pi squared divided by 12, t divided by tf squared to the minus 2. Okay. Let me check if this is correct. Questo qui è quello là, vabbè. 1 plus 5 half. Okay, good. Now, let's make the following, let's consider the following facts. So here you have a P divided by KB, and here you have a lambda cubed, which is T to the minus 3 half. And therefore here you have something like P divided by KB, T divided by KB, T to the power of 5 half, proportional. I'm taking the proportion in order to keep, well, to avoid all the prefactors, which anyway I'm going, one can check it, must reproduce the t equals 0 case, but it's quite boring to do this. So let's be a little bit more smart. And so here you have a P, which is divided by KB, T to the power of 5 half coming from the lambda. And this is proportional to a quantity here that is, it has again a T1 divided by T to the power of 5 half, which is in here, times TF to the power of 5 half, apart from the prefactor. And then I have all these guys here, which are 1 minus pi squared divided by 12, and let me call this quantity x squared, the power of 5 half. And then I have 1 plus 5 divided by 8 pi squared. This is x to the minus 2. Then I have 1 minus pi squared divided by 12, x to the power of 2, and then this also to the power of minus 2, where x is defined as t divided by tf. Okay, t. So from this, you see that the T5 half and the T5 half drops. Then the pressure is a KB. So the pressure is equal to something which is KB to the power of 5 half, TF to the power of 5 half. I'm just considering the important quantities, so not all the prefactors. Then I have here, I can expand, considering that x is very small. This 5 half goes here and becomes 5 divided by 12. So here I will have 1 minus pi squared, x squared, and 5 divided by 12. 12, sorry, 24. 24. 1 minus 5 pi squared, 24 x squared, yes. Then here, let me see what I get here. This is TF. Well, actually, this is x squared because x is t divided by tf, and this tf divided by t. So then I have 1 plus 5 pi squared divided by 8 x squared, and here you have another correction, which is 1 plus pi squared times minus 2 divided by 12, with the minus becomes 6 x squared. And I think that's all. Okay, let me check. I get 1 meno 5 24esimi, 5 ottavi squadro, 1 più pi greco 7 squadro. Okay. Now we can work out at second order. We keep the second order terms in x. And so basically you take this expression, this will be 1 plus some number times x squared, and you neglect all the other terms. Okay, if we keep just the number in x squared, you get this guy times 1 and this times 1, and if you do the calculation, which are trivial, you see that this is 1 plus, write the result, 5 pi squared divided by 12 x squared, which is t divided by tf squared. Okay. Basically, one has to keep, one has to do 5, 8 minus 5 divided minus 5 divided by 8 minus 5 divided by 24, and one gets this number here. It's this one times this one. Okay, so therefore at the end I can write the expression for the pressure. That will be the t equals 0 expression that I can just copy. Of course, one can do the calculation completely, but it's boring. In any case, we should recover the t equals 0 case, which is the following. Then I have a 1 plus, and here I can now introduce the correction in t, which is 5 pi squared divided by 12, and t divided by tf to the power of 2. Okay, so it's a positive correction that provides me an additional contribution to the pressure as the temperature is increased from 0 to a finite but small value. Okay. Now this expansion, if one complete it, is called Sommerfeld expansion. To which we have taken just the first correction, which is a t squared correction. One can go on and expand the quantity 1 plus t to nu to the power of 5 out. You can expand and keep other terms, and you will get all the correction to the equation of state, or to the relation between mu and the Fermi energy as we do the final temperature. So some of the function. Now we can also compute, which is the relation, which is the correction to the internal energy as due to this final temperature. Well, basically, there's nothing to do, in the sense that since PV is equal to 2/3 U, you see that pressure and U are proportional, and therefore we expect that U divided by N will get also the same contribution. So this was 3/2 times the Fermi energy, and here we will have 1 plus, again, the same correction, which is a 5 pi squared divided by 12, and tf squared. Okay, so this is the first correction to the internal energy per particle. And then also we can see what happens to the CV divided by KBN, if you want. This is the derivative of U with respect to the temperature. And of course, now this quantity, I just need to compute, so this is a fixed volume. This is just, well, this guy here, so it's 3 half, l'ho fatto così, si pensa di sì. This is messo il KB, l'ho tolto. Sorry, okay, let's do the following. CV is the UDT, okay, then I get, I divide by M, and so I get this one. So now, then I can add the KB afterwards. Okay, let me just compute the derivative of this quantity here. And what do I have here? I have 3 so 3 divided by 5 EF. Then I have a 5 pi squared divided by 12. Then I have a 2 T divided by TF. And 1 divided by TF. Okay. You see something pops. Then I have 3, 6, and 12, so factor 1/2. Yeah, so I have pi squared divided by 2. Pi squared divided by 2. Then I have a Fermi energy, pi squared divided by 2, a Fermi energy, a T, and here I have a PF squared. But EF is equal to KB TF. So this is KB TF. Okay, so this guy will be removed. And I can also now put a CV, a KB can be put in the first term here. So then I get finally the CV divided by KB n in order to have a high-dimensional quantity is equal to pi squared half T divided by TF. Now, this is the important thing. One has to remember, apart from the calculation, of course, it's a little bit tricky, but the most important thing that one has to remember is the correction to the pressure, to the internal energy, as to the final value of the temperature, and therefore, also the linear behavior of the heat capacity per particle at small temperature. Okay, as opposite to the case of bosons, for massive bosons, the heat capacity was scaling as T to the power of 3 alpha, as we have obtained the last time, well, last week maybe, for the boson gas at small temperature. Whereas for fermions, this is linear. Okay, so the contribution to the heat capacity as due to the electrons, for instance, is linear in T, whereas the contribution to the heat capacity as due, for instance, to phonons, which are the vibration of the lattice, are proportional. Well, actually, in that case, it's even different because they are massless. And in that case, the behavior is a little bit different. We have not computed, but should be T to the power of 3, as for the case of photons, actually. So for massive bosons, it's T to the power of 3 alpha. For massless bosons, it's T to the power of 3. Okay, so this is the heat capacity. This is an important result. And I think I need to comment on another point. which is the following. Now the pressure gets a contribution which is order of T squared when going from zero temperature to finite but small value of the temperature. Now the entropy can be computed as the derivative of the pressure with respect to the temperature. Entropy is proportional to the derivative of P with respect to T, because P is proportional to the ground potential. Actually, PV is minus the ground potential. We have done the same calculation for bosons, and therefore the entropy is proportional to the derivative of P with respect to temperature. Actually, this is the entropy density, and therefore you see that this is linear in T. Therefore, this also goes to zero as T approaches zero, which is again the third principle of thermodynamics. So also for fermions, the entropy is going to zero as T is going to zero, as in the case of bosons. Now, in the case of bosons, maybe the result is more intuitive in the sense that all the particles are in the ground state, and one can expect that the entropy is vanishing because they are all in the same state. Here is a little bit tricky because there is the exclusion principle, and therefore the particles actually occupy different levels, energy levels, but nevertheless the entropy is again going to zero, also for the case of fermions. Okay, that is also a reason for computing the first correction for the T equals zero result, because in that case one can also see what happens to the entropy and to the behavior of the specific heat at small temperature. Let me make another comment and then I stop here. That the behavior of the heat capacity, this formula here, can be somehow understood by using the following argument. So when T, so suppose that here I plot the distribution, the Fermi distribution, Fermi-Dirac, as a function of epsilon q. Now, for T equals zero, we said this is a theta function. Okay, where this is the Fermi energy equal to the chemical potential. When T is large, well, when T is increased from zero to a finite value, what happens is that I have somehow something like that. Okay, so I have a depletion of these levels below the Fermi surface, and I will start to occupy levels above the Fermi surface. Okay? So we'll have this smooth behavior of the function. Now, this region of depletion and occupation of the energy around the Fermi energy, it is of the order of kVt. Okay? So that means that when I compute which are the, let's say, degrees of freedom that can be excited when providing heat to the body, basically the degrees of freedom are which are active is something like n, which is the number of particles, times the ratio between T and Tf. Okay, which is basically this region here, kBt, divided by kBtTf, which is which is the ratio, if you want, between the particles that can be excited and all the particles. Okay, so somehow this is the fraction of active degrees of freedom times n, which provides the total number of degrees of freedom, which is the energy of those degrees of freedom, they have high energy of the order of kBT. So each of them energy of the order of kBT. Okay. Therefore, I can basically assume that the internal energy, as the variation of the internal energy as due to those degrees of freedom that are active now close to the Fermi surface, is proportional to T squared, as you see from here. And therefore the heat capacity will be proportional to T. Okay? Because just the derivative. So one can infer the behavior of the heat capacity at small temperature also by making this kind of argument. So counting basically the number of active degrees of freedom, which will be the total number of particles times this fraction. And each of those particles will have an energy of the order of kBT, and therefore the internal energy associated with those degrees of freedom is of the order T squared, and the heat capacity is of the order T. Okay? All the particles that are below, far from the Fermi surface, are not excited, cannot contribute to the heat capacity. Okay, so all the particles, so the dynamics, the response, basically, maybe better to say, of the body is provided by the particles that are close to the Fermi surface at T small. And now it's 1, and better if I go to this, it's quite heavy. Okay, see you. Ciao.
Arrivederci.
Allora.